All right, let's talk about why this is so important. So, according to the CDC, there are about 1.35 million people killed on the roadways around the world each year. And these are preventable things like drunk driving and drowsiness, distracted driving. So, what we're really trying to tackle here is distracted driving, and especially these aggravating factors like not wearing your seatbelt, which make things so much worse. That's what we're trying to solve here. So what we're trying to do with Iris is build some sort of system to help people keep from being distracted. And the way that this would take form is probably some sort of camera on your dashboard or maybe in other places around your car that would be able to scan you and see if you're wearing your seatbelt, if you're on your phone, if your eyes are not on the road, things like that, which would be able to like tag you and maybe ping your cell phone or help in case you got into an accident and needed to submit that to your insurance.
Did work around distracted drivers and seatbelt detection. As an example, Chen et al. Developed an application that used convolutional neural networks to detect the if a driver and passengers were wearing seatbelts. And so they found that convolutional neural networks is the best um, neural network to for this type of application. And in general, for classification, it seems to be the case that CNNs are the best at doing this. Uh, there also exists the YOLO architecture from Kashevnik et al. In 2020. And YOLO has been around for a while, but it's a variation of a convolutional neural network, and it stands for you only look once. This network architecture provides a significant performance boost over convolutional neural networks because it's optimized for real-time applications. And so we looked at this and we this is an option to optimize our CNNs even further. Also, work by Vicente et al. In 2015 found they did 3D rendering of head and poses to try to predict driver behavior. But we decided that this was all too complicated for our use case. But there is one way of having more accuracy. Finally, work by Viral et al. 2007 developed a system that used 30 different classifiers to detect particular behavior. And so this is actually something that inspired our work. And so we decided that this system was simple and it was scalable to some degree. And so this is what we decided to sort of recreate.
So in building our two models, we used two very different data sets. One of our data sets came from a Kaggle data science competition hosted by State Farm to try to detect how drivers were distracted. This data set had over 22,000 images for the training and validation set, and there were tens of thousands of entries and $60,000 or more on the line for the best model. So this data set was very professionally collected. They varied all of the categories of things that you might need in order for a model to be practicable and effective in the wild. So they had people of different ages, sizes, skin tones, hair colors, wearing different types of clothing, and in different types of lighting conditions. So very professionally collected, very regimented, so that they had a great diversity of images so that the models that were created would be as useful as possible when deployed in an outside setting. And so we also wanted to tackle a much more novel and simple problem of just detecting whether a driver's seatbelt was on. And we knew that we would have to take this model from start to finish. There would be no existing data sets, which we found quickly through searching online. And so we had to take matters into our own hands and try to collect data ourselves. And we tried as best we could to replicate the methods and procedures we'd seen in the Kaggle State Farm data set, but this just proved very difficult. We had much more limited access to participants, and that just limited our ability to vary some of those important factors like ages, skin tones, different qualities of appearance like eyewear, clothing, things like that. And we tried our best to vary these as much as we could and create a diverse set of images that would create the most robust model, but it was still more challenging than we expected it to be. And so in comparing our two models, we found that this is a great source of difference, which popped up in both our ethics discussion as well as the discussion of our results in the end. And for both of these data sets, we conducted the classic data transformations and data augmentation steps using the functions available from PyTorch. So doing things like rotating, cropping, shifting, normalizing pixels so that they would work with our transfer learning models.
Okay, let's talk about how we're going to do this. For basically all of our models, we used PyTorch because we've been using it in class and it has a lot of cool tools. We didn't want to reinvent the wheel here. For both of our models, we built CNNs from scratch, adding layers by hand. We also compared them to pre-trained CNNs which PyTorch provided via their ResNet 18 architecture. And for both these models, or for one of these models, we used images just captured on smartphones. So we had like friends and family go into their cars, and we took pictures of them pretending to drive. For the other one, we used the Kaggle data set, and that was the State Farm model that we called.
Okay, now we'll run through a demo of our from scratch model to detect whether drivers are wearing their seatbelts or not. So we're using a folder of images compiled by Ruben that were not used in training. They're a new set of images, completely unseen by our model. Oh, look how handsome. And so we have a set of 20 of those, 10 of which are belt on, 10 of which are no belt. So we'll kind of go through the regular steps of adding our hyperparameters, transforming the data, loading it in, and now we'll run it through our model to predict. This will just take a second or two. And then afterwards, we're going to print out the model's predictions. And we can see the images look a little funny because we're still using the transforms from when we're training to normalize images. But immediately off the bat, we see that our model always classifies as belt on. And this is one of the challenges we had with our from scratch model. You know, sometimes depending on the way training worked, it would take it in one direction or another, where it would classify it as always belt on or always no belt, or sometimes come in between. And so this is an example of a training run where our model classified a lot of images having belt on, even though, as you can see here, he's not wearing a seatbelt. And we've varied a lot of characteristics such as the angle and where Ruben is looking. So yeah, this is an example of some input that didn't do exactly what we were hoping, but it's what happened from our homemade data set. Okay, so now we'll demonstrate our State Farm distracted driver model. So similarly, we'll use a folder of images that our model hasn't seen before. These come from the test set from the Kaggle data set. Similarly, we use all the hyperparameters from before, same set of transforms, load in the data, give it to our model, let it make the predictions, and then we'll visualize. So as we can see, sometimes our model gets it right. We predict safe driving correctly, but here we predicted hair and makeup when the person is driving safely. We get texting right correctly, talking on the phone right correctly. But you know, there are some misses, but a lot of accuracy. This is one of the things that we see from this model. It's much more consistent, and it does a better job really on what is a tougher classification problem. And we can attribute a lot of this to the data sets that we were able to compile and use.
Okay, and lastly, let's talk about ethics. So there's a good reason that we don't want this published quite yet. And the main factor here is that Adam, Ruben, and I are all kind of Caucasian young males. And we're worried that this data set is going to skew our results so that the model only really works on this demographic. We don't know how it'll work on people with different body types. We don't know how it'll work with people that have different skin colors. And that's a big concern for us, especially because we want to be inclusive and we want to make sure that we're accurate. So we don't know what the accuracy is going to be for other groups. And with that comes privacy concerns, because you're going to have a camera in your car, and that's not a small thing to ask people to do, especially if we're not sure that our model is accurate. But one of the big things that we came across was the question of who's going to be able to delete that data or mess with it. And if it's just the driver or the people in the car, that's great that they have that sort of autonomy over their data, but it also means that they'll be able to obstruct justice a little bit more easily. And you know, if they weren't wearing their seatbelt, now they might get away with it because they were able to delete the data and sort of lie to the justice system. On the other hand, if someone else has that data, that's a huge concern because either a company or maybe the government kind of owns the video inside your car, and they're probably going to, put forth some laws to make sure that you have that thing on. Lastly, we have financial concerns because you do have to have some sort of camera or even cameras inside your car to make this thing work. And that's probably a burden that's going to be passed on to the user. We don't want more financial burdens being passed on. We already know that owning a car itself is a big burden, and we don't want to make that worse.
If we had more time to work on Iris, we would definitely invest it into curating a more diverse data set that is representative of the general US population. Although we have developed a model that detects if drivers are wearing seatbelts with fairly high accuracy, most of our sample contained white or lightly complected people, which is often a problem in image classification and just in general machine learning applications. So, because of this, I think we would see the most improvement in creating a more robust data sets. In addition to all this, there are other classification problems that we'd like to solve in the future as part of Iris's broader goal of increasing driver safety. And these classification problems include driver gaze detection, passenger seatbelt detection, and passenger activity detection, all to provide more context to the computer that is monitoring cabin conditions. A long term goal is to deploy this as an in cabin system that provides real time analysis by running all of the neural networks in parallel.